Thank you very much. So, I'm Heshou Zhang. I work in Italian National Institute for Astrophysics in the Observatory of Brera. I'm honored to give the talk here about the non-thermal radiation related to the magnetic halo of the Milky Way. And I want to use this opportunity to thank my collaborators, especially Gabriele Ponti, Ettore Carretti, Roy Liu, and Mark Morris, who teach me X-ray, radio, gamma ray, as well as the galactic outflow science. So my talk will be based on this paper. This is our recent paper posted on arXiv last week. Please have a look. This is the QR code generated yesterday. I learned from you. So, and also my funding source. I want to acknowledge them as well. So, sorry. I'm sorry. This is not working somehow. Okay, I'm gonna use this. So we are in an era blessed with all sky surveys from different bands, from the radio to polarized dust emission, and I want to bring your attention to the X-ray and the gamma ray. So the X-ray from 0.6 to 1 keV, we have the E Rosetta bubble observed by the E Rosetta satellite, and extending up to more than 80 degrees in galactic latitude. And also, more than 10 years ago, there's the detection of the Fermi bubble observed by Fermi satellite, and this is in gamma ray band. These two seem to originate from the central part of the galaxy. But when we have all those all-sky map with those very gigantic structures, can we simply say that where they are? I mean, these are broadband emissions, and we might not have the information for that. And when we see gigantic structures, they are also possible to be something very close by, right? If we don't know the distance. So this brings us to this comparison. So here the green one is the E Rosetta bubble. The white ridges, so they are the magnetic field line measured from the synchrotron polarization at 23 gigahertz. As you can see, there is a consistency between the E Rosetta bubble with the magnetic field line, where you have the magnetic field line parallel to the edges of the E Rosetta bubble, as well as the red background is the polarized intensity, so it has a similar enhancement at the edges. And can we stop our talk here and say, oh, look, there is a magnetic halo corresponding to the E Rosetta bubble. That's it. No, we cannot, because we are observing the sky without knowing where they are. Actually, more than 50 years ago, these radio structures, especially the North Polar Spur, has been observed, and it has been assumed to be a local structure within the local hot bubble, like 50 to 100 parsec, showing that it is some, like, there's a simulation like ancient supernova explosion remnant structures. Are they? Well, let's see. So this is the geometry that I want to talk about. If you observe something very gigantic in the sky, it can either be within the local hot bubble, 50 parsec, or it can be 5 kiloparsec, and this would stand out of the galactic disk. What's the difference between these two if you look at them? Like observationally, this thing, if the signals from there want to transpose to us, they have to go through the disk. So if something like this happens, then the disk should imprint itself onto this emitting structure. Let's see what happened with the synchrotron polarization emitting structure. So if you have some magnetized structure that emitting polarization signal in radio band, then your polarized signal will suffer Faraday rotation as it propagates through the magnetized ionized medium, and it's proportional to the line of sight density as well as the wavelength. As a result, if you have a line of sight turbulent magnetic field, which you do have in the galactic disk, of course, much stronger and much higher electron density than the halo, what will happen is at a lower frequency, it suffers much more than the higher frequency from the Faraday rotation effect. And if you propagate long enough in the disk, the polarization signal of low frequency will be depolarized. It will be destroyed, whereas the high frequency still sustains and you can observe it but not the low frequency. This brings us, if we have three frequency, with the low frequency, medium frequency, and the high frequency, you will separate this emitting structure into three regions. Region A, it doesn't penetrate through the disk much, so all those three frequencies can arrive at us. Region B, not so much for the 1.4 gigahertz, but the other two higher frequency can arrive at us. But for region C, because it propagates so much in the disk, so only the highest frequency can arrive at us. Let's look at the observation. So, look, this is our expectation based on our knowledge of the magnetic field in the disk and the electron density in the disk. What would be the Faraday depolarization screen look at 5 kiloparsec? And this is the observation for the three corresponding frequencies. So 1.4 gigahertz, you have a Faraday screen around more than 20 degree latitude. And 2.3, you have a Faraday screen of 5 degree latitude. Look, A is all bright. B, only the higher frequency are bright. C, only the highest frequency is bright. So what happens is those structures corresponding to the irreducible bubble. So then you can see that these regions actually, comparing to the lower frequency, you have a symmetric depolarization screen, and this must come from at least 5 kiloparsec away from us. So they are galactic. But this local structure, you see, this is a known local structure. They stand less than 1 kiloparsec from us, and they are not suffering from this Faraday rotation screen. So in those two frequencies, you see they look very similar. We know the magnetic field, these regions coming from much far away, like 5 kiloparsec scale. Then what happened in the X-ray? I want to bring your attention to this figure, which is the irreducible bubble stance. So this is the X-ray. And we compare it with the dust from us to 500 kiloparsec. You see a nice anti-correlation between the dust structure and the irreducible bubble, which indicates the irreducible bubble, because the dust will absorb the X-ray photons. So the irreducible bubble should also stand beyond the galactic disk. Then we come back to this comparison. Now we are much safer, right? Now we can say, look, both the magnetic filaments and the irreducible bubbles, they stand beyond the disk, and they consistent co-spatially. I promised to mention about NGC 891 yesterday. Here we go. Look. This is the X-shaped magnetic field detected in NGC 891, Heshou Zhang galaxy. And this red one is the X-ray halo beyond the disk. So you can see that it also stands out of the disk. Something similar to this. Can it be the same? Let's go further. So what we do, the synchrotron polarization, it is a result from the relativistic electron. When you have a relativistic electron in the halo, what happens? Because the disk has so much starlights and from multi-wavelengths, and also there's a CMB. Naturally, you expect some gamma ray photons due to inverse Compton procedure. And this is with more than 12 years of Fermi data. Not only do you see the Fermi bubble, but if you compare this region 0 with the significance of all sky, you see that there is a 5 sigma significance compared to the background, which corresponds to the irreducible bubble, which indicates, so you also have a gamma ray counterparts of the irreducible bubble. And this brings us to what all these wavelengths can teach us. Here we go. Well, the relativistic electrons, when they generate around the magnetic field, they will emit synchrotron radiation, and here there will be inverse Compton. Putting these together, you can see that we take a patch 1 and patch 3. You see they can fit with a single power law distribution, and their magnetic field strength can be constrained 1.5 to 2 microvolts at this height, and they are in high beta regime. The plasma beta in 1 and 3 are around 10. They are symmetric. This brings us to the comparison between the magnetic ridges with the star formation rate on the galactic disk. So this is from Heshou, and you see there are some high star formation clumps on the disk in the central part, which if we project it onto the disk, there are some high star forming clumps with which is like a 3 to 5 kiloparsec away from the galactic center. If you look at the magnetic ridges, not everything is from the galactic center. The irreducible bubble, the Fermi bubble corresponding ones connects to this black dot, whereas the other ones connects actually to a few kiloparsec away from the center. What does this tell us? this tells us that, well, our Milky Way, there is an central outflow, which is the gamma ray Fermi bubble, connecting it to the chimney and then to the galaxy center. And then there's an outer outflow, which connects to the star-forming regions 3 to 5 kiloparsec away from the disk. And these corresponding to the E Rosetta bubble, which is the outer outflow. So there's an inner outflow and outer outflow. So this is the geometry that I simplify. So it's kind of like this. If we look at the magnetic field line and consider that as you grow to higher latitudes, you have a decrease of rotation velocity. If we take this into account, projects all those different heights onto the 2D map, what will happen is you see that the magnetic field line seems to naturally tilt from east to west. And that indicates the magnetic field line traces actually the outflow dynamics. So this brings us, and we check the energetics. So it needs like the outflow injection rate is like 0.3 to 1 solar mass per year, and the energy needed for the supernova explosion in the star-forming ring is only like a few to up to 20%. The take-home message I want to give you is, first of all, there's an inner outflow, which is the Fermi bubble, and there's an outer outflow, which is the E Rosetta bubble. So these, they may have different dynamics. The foot points are quite separated for the E Rosetta bubble. And also the magnetic field line, which is filamented, coherent, tracing the outflow gas. Why it can survive to such height, we have no idea. There should be future studies for this. And this is our paper. Here's a QR code. Thank you very much.
Very much thought. Very interesting. We have time for a few questions and comments, please.
Interesting results. I have two quick questions. First, can you comment on the gamma ray formation mechanism? Is it the same for E Rosetta bubble and Fermi bubble? And second, can you comment on the time scale of the E Rosetta?
Thank you very much. This is a very nice question. First, about the gamma ray. So what we do, I should show you the SED. So we do the multi-wavelength SED for gamma ray as well. Here, we compare like region 5 and region 3. So this is the Fermi bubble. This is E Rosetta bubble. First of all, we check the cooling time. From the disk up to here, the TeV electron will be cooled. So it needs a real acceleration. But if we consider the cosmic ray coming from here to here, you see the power law of gamma ray here and here are quite different. And so inside the acceleration mechanism might not be the same. And also because of the parallel magnetic field we detect compared to the shell of the Fermi bubble, it is very difficult to diffuse out for the Fermi bubble to inject. So maybe they are different. We are not sure. That's our consideration. Second, about the time scale. We think that we cannot tell about the Fermi bubble, but for E Rosetta bubble, we actually check the time scale from 10 to the 8 to 10 to the 9. We find that with current star formation rate in the ring, like all those different time scales can sustain the E Rosetta bubble. But because what we see is a projection effect, so we cannot actually tell specifically what is the time scale. That needs future study to check. Thank you.
Thank you. Any other questions or comments for Heshou? Oh, one, yes, please.
Have you looked at whether there's enough star formation in the bar to power what you're saying the E Rosetta bubbles comes from? Is there enough, clusters and energy from the stars?
So that's a good question. So what we check is that this star formation rate is measured from Heshou. So it's from the infrared. What we will future compare is if there are there are also other star formation tracers, like counting the number of stars in different and that might give a different results, we believe, comparing to this one. So we need to check. But talking about bars, I think it's not just the bars, it's the whole ring at 3 to 5 kiloparsec that will power this. If it's only the bar itself, it's still not enough. But considering the foot points is this scale, we think all of these should take into account. Probably they can contribute to the whole feedback as a whole. Yeah, thank you.
you for the question.
Any other questions or comments? Okay, let's thank all the speakers in this section one more time.